Okay, we're going to go ahead and get started here. Who remembers Dr. Pollock's presentation from last year? Yeah. There was a section in there where there was like a water battery which had no electrolytes in it. All it was water, and it was lighting up an LED. I don't know if you showed pictures of it, but I know that it was discussed. And it's about, you know, the easy water separates, there's a negative and a positive, but there's no electrolyte in it, and you series those up, and you're actually getting electricity out of it. That battery was invented actually by our next presenter. So Kurt has a BA in wireless communication engineering from a national university in Taiwan, and he holds a master's of electrical engineering, an MBA certificate in technology entrepreneurship, and 2 PhDs in electrical engineering and nanotechnology from the University of Washington, where Dr. Pollock is. Kurt's experience includes microwave electronics, nanotechnology, and rapid prototyping. During his PhD, he developed a prototype to harvest energy, which I just mentioned, from clean water based on fourth phase water properties. Kurt has been involved in research and technology and development and businesses with startups since 2012. In 2016, Kurt founded a company, Fourth Phase Incorporated, along with Dr. Gerald Pollock and Dr. Chris Gronitt. Besides the over 1.5 million seed capital that was raised, Kurt was recently awarded with the NSF SBIR for a $250,000 non-dilutive research grant for Fourth Phase Incorporated. So welcome Kurt Kung.
Thanks, Aaron. Thanks. So Professor Pollock, who's my PhD advisor back in the time we still worked together, so he discovered this interfacial water, and two very distinctive property of the water is, first, exclude the small particles away from that little water zone, and we later on call it exclusion zone water. Part of the reason why, so it's a microscopic image. On the right-hand side is hydrophilic material. In this case, we use a polymer called naphthalene. We're going to talk about it a little more later. And on the left-hand side is basically just water with small particles in micron size in diameter, and people usually call it microsphere. So what happened is if you have certain material, usually hydrophilic material, by the way, hydrophilic means water love. So when you have something that water would actually be attracted to, that we define hydrophilic. On the contrast, that will be hydrophobic, like the lotus leaf. So when you have a hydrophilic material in the water, water will spontaneously repel the contaminants, the impurity, and push it away, further away from the interfacial area. So this is the hydrophilic material I was talking about, and here is just the water, and the little black dots here is the microsphere I mentioned. So this is a still image, but I'm going to show a video later. So that's why we dub it the exclusion zone, because it excludes the impurities, the particles, the contaminants. And the second very noticeable property of interfacial water is the net negative charge. So here on the right-hand side, just imagine it's the same material. In this case, we use naphthalene. If you place the electrode in the water, we're going to show more detail later, that you can measure the electrical charge, the electrical potential, up to about minus 200 millivolts. And if you move the electrode away from the surface, then the potential drop, the amplitude of the potential drop, and go back to eventually neutral, zero. So here is a quick video. It's just constant looping by itself. But in this case, it's rotated about 90 degrees. So you have the easy generating material polymer on the top, and you have the water with small microsphere, and spontaneously just get pushed away. And this video is 6 times faster than real time. But no matter what, you get a good understanding like why we want to call exclusion zone, because when we see the phenomenon, it's just mind-blowing the first time we saw it. Say that again? So the question is why there's pulsation. It's an excellent question. So these are the phenomena that we observe. And along with the net negative charge we're going to talk about, which lead to the water battery discovery, those two evidence lead us to believe that water has a structure at the interfacial region. And because of the structure, it stores net negative charge. So you must wonder so far, so if you can create charge separation in pure water, then where is the energy coming from? What is the original energy source make water able to separate the charge, and therefore we can potentially tap into that energy source? So it turns out that we find this is another microscopic image on the top. In this case, it's PAHL, not naphthalene, but it doesn't really matter. It's a easy water nucleated material, and you have the microsphere and the zone that without microsphere as a marker that we use indicate where is the exclusion zone. So once you have this, it turns out that if you shine infrared light, really, really weak infrared light, no more than 10 microwatts, but you can precisely locate the light at where was the exclusion zone, and within few minutes, no more than 3 minutes, I would say, we would usually observe the exclusion zone expand like up to 10 times of its original size. So that's pretty cool. Indirectly that we confirm infrared light is the energy source, original energy source, make this charge separation happen. To echo the gentleman's question earlier, the way I like to think about it is the root cause of everything of the interfacial water or easy water is the structure, the semi-crystalline-like structure. It's not technically semi-crystalline, so you have to say it like. It's similar to the semi-crystalline structure, and because of the structure, once you build up the structure, just like when when you turn water into ice, exclude the impurity outside of the body of the ice. At the same time, because of the structure, it yields net negative charge, which is not the topic we talk about today, but I do have slides in my appendix. If we want, we can talk a little bit about it at the end. First thing, this is the first set of experiment which I used about for four years. It's a micropipette electrode. Micropipette electrode is a glass capillary tube. You heat it up in the middle, you pull on both ends, eventually it breaks, and it forms a very sharp and needle-like geometry. And you can use that to do very fine measurement to measure potential. In biochemistry, it has been used a lot. So when we have this electrode, and then we can properly mapping out the property of in a charge density, the electrical property of water and the charge density around the interfacial area. A little bit more detail inside the glass electrode, the glass needle. Originally, of course, it was empty, so we have to fill it with 3 molar KCl solution, potassium chloride solution. So Aaron mentioned earlier there's no electrolyte in the system. It's semi-true, there's no electrolyte in the water, but in the electrode, we do have some electrolyte to convert the ionic current into electric current, which we're going to talk more later. But here's the process. The glass micropipette electrode connected to a half cell, which has the silver chloride metal at the end in contact with the potassium chloride solution, same as the reference electrode. So what happened is because of the charge separation and potential gradient, silver will tend to react with chloride ion, form silver chloride, and then generate extra electron, go to the external circuit. And the electron has been generated from the anode, goes to the cathode, and combine with silver chloride and form silver and chloride ion. That's the whole circuitry. It is really that simple.